Right, good morning, everyone. As usual, how did the homework go? Okay, so all right, so we can go through them, and but this time, as I go through them, I want every time I'm going to give you a minute or so for every one of you to interact with the problem and tell me how to do it. So you have to participate a lot to get through this section. So number 8. Number 8, what is it? So we have to find the antiderivative of the following function by substitution. Yes. Okay. So the idea of substitution, they take care of integral where that should be the picture, where we have a function and its derivative is also part of the integral. So we have an inside function or an inner function, which is 4x squared plus 3, and its derivative, which is 8x, is also part of the integral. That's really where substitution has to be used. All right, so I will do the first one, and then, as I said, after that, I want you to do it in front of you, and then we check if you guys get it right. So how does it work? We introduce a variable, we call it u, and u is usually the inner function or the function whose derivative is part of the integral. So the u is the 4x squared plus 3. That's my u. Once you find a u, you have to express everything within the integral in terms of the new variable. So you imagine now you have a new variable u, everything here has to be in terms of u. So to do that, since I have a dx, you compute du dx. It means the derivative of u. This is 8x. It's not working. Then you multiply by dx. And you get the du is 8x dx. And du usually is called differential. And dx, to make it real for you, think of dx, that's the delta x. So which make it real for you. So it's not like symbolism, because from the Riemann sum, we know that the dx actually represent the delta x. So that's how you should think about it. Now, everything within this integral, when I say everything, I mean everything, has to be in terms of u. Means we need to create another integral here in u. Should be no more x. Everything should be substituted. Now this can be taken care of it immediately, because this is the cosine of u. Now what's left? Now what is left is 8x dx. And this also has to be in terms of u if possible. But always we have to keep looking here and here. We have always to connect those things. 8x dx, it's verbatim the du. Once I have an integral in u, nothing but u, I evaluate it as an integral in u. So now I have a new one, the new variable in u. This one should be easier than the first one. So as an integral in u, the antiderivative of cosine is the sine of u plus c. Once I evaluate this as an integral in u, and then I go back to my initial variable, because this integral is a function of x. So my answer has to be a function of x. So this will give me the sine of 4x squared plus 3 plus 6. So it's basically the antiderivative of this function, the antiderivative of that at 4x squared plus 3. Okay, and now we can check. And that's when you see that we are actually reversing the chain rule. Checking means we find the derivative of this function, and we make sure we get the integrand. So if I find the derivative here, give me equal to chain rule. That's an inside. That's the outside. So it's the derivative of the sine, which is the cosine evaluated at the inside times the derivative of the inside. That's the chain rule, which is exactly what we wanted. Times 8x. Okay. All right. So now number 12. Number 12. Okay, that's a good one. We have to find the antiderivative of e to the 3x plus 1. Okay. Again, as I said, I will want to give you a minute to think about it, and then I will get back to you. Please, if you have a piece of paper in front of you, do it on a piece of paper in front of you and see how far you can go. So I'm going to keep quiet for a minute if I can do that. Those with answer, put them on chat. Anybody with answer? Okay, anybody else? Anybody beside the student that everybody see her name?
I got 1/3 e to the power of 3x plus 1 plus c.
Okay, guide me. What did you do?
All right, so first I identify the u of the problem.
The u. What is the u?
3x plus 1.
That's my insight, basically. You know, because the only thing I know is the e to the x dx. That's ex. That's it. Okay, now I have something here. That's immediately we have an inside function. All right, and then the derivative is not part of the integral. It's not a big deal because in this state, the derivative is a constant. Only when the derivative is a constant, it's not really part of the integral because we can take care of that. Otherwise, it has to be. All right, keep going. What's the du?
The du turns out to be 3 dx.
Right, is the derivative dx. The x, remember, is a delta x. Don't act with it like it's something weird. Think of it as a delta x. So you don't, so like it like an object. It's not like nothing. All right, and then what do you want me to do?
Then you divide each side of the du equal to 3 dx by 3.
Right. He has to do that because when we keep watching what's going on, we know that there is not the third as part of the integral, but that's not a big deal. We can really take care of that. Now the substitution and the verbatim. What this gonna give me?
First, you replace e to the power 3x plus 1 with e to the power u.
Took care of that.
then you multiply e to the power u by 1/3 to the power 1/3 du.
1/3 du. Verbatim. We have to do it verbatim. The substitution has to be very clear. You're substituting. That's where the word substitute comes from. And now, of course, he is done. If third is a constant, I can take it out. E to the u du. That's going to give me a third antiderivative of EU. EU now at this stage that's an integral in U. So you forget a little bit about X. That's a new integral. The variable is U. You evaluate it. Plus, and then you can check, which is not check. You guys check it because it's a good practice for the chain rule. All right, so let us proceed. So I'm thinking of those problems as a drill problem for you to totally get substitution. Okay, now let's look at number 19. What is it about? 19. Okay. Again, that's the integral of 2x squared over the square root of 1 minus 4x cubed. Again, you have to, again, I'll give you a minute. You look at it, stare at it, do whatever you want. Identify the u by picking the function who is the part inner, part, its derivative is part of the integral in a way. Okay, anybody ready? Okay, who's ready to talk about it? Like what your classmate did a minute ago. Who's ready to talk? Don't shy away because I don't know who you are. So just talk. Who's ready? Please, we have a lot to talk about. Speak up. Okay, so we're gonna rewrite it as to the power minus a half dx. Okay, it looks scary, but actually it's not. So now we look at it. Do we have an inside? And the derivative of the inside is also part of the integral up to a constant. There is always a constant that we don't worry about it. So what is going to be my u? Here, what is my inside here? Quickly, guys. Okay, that's gonna be my u. Because the derivative of u, it's 12x squared. As I said, I have the important part. I have the x squared. The constant never really it's not a really big deal for me. So I'm going to put my u to be 1 minus the 4x cubed. And then my du would be the derivative of that. The derivative is minus 12x squared dx. And now I have to do the substitution. Okay, so this is equal to integral of, the 2 is not, okay, the easy part. This is u to the power minus a half. Now x squared dx, the 2 I'm going to keep it because it doesn't seem to show up anything. Now the x squared dx, I can pull it immediately from here. So I want the x squared dx, I divide by 12, by minus 12. So minus 1 over 12 du is x squared dx. We're really substituting verbatim. So the x squared dx is minus over 12 du. That's the piece I want. So now I'm listening.
Can you just do negative 1 over 6?
Absolutely.
Okay, you could do that too.
Absolutely. It's substitution. Okay, so absolutely you can do that. Okay, so now, absolutely. Now 2 times actually you're going to get it right there. That's a constant times minus 1 over 12. That's going to give me minus 1 over 6. U to the minus a half du. Now I have an integral in u, only in u. It's way easier than the mess I had at the beginning. This new integral in u should be easy to compute. Okay, so now this is going to give me minus 1 over 6 times 1 over minus a half plus 1 u to the minus a half plus 1. Now minus a half plus 1, this is nothing more than a half. So I flip it, I will get minus 2 over 6 u to the half plus c. What's going to give me minus a third. At the end, I go back to x. And 1 minus 4x cubed to the power a half plus c. End of the problem. Let me give a small remark. The substitution would fail. Did fail. The minute, the substitution is really very delicate, but at the same time, it's an extremely powerful tool. So it's very delicate in the following sense. If instead of 2x squared, I have 2x cubed here, divided by 1 minus 4x cubed, if I change a little bit, instead of 2, I have 3. Sorry. Substitution will not work anymore. We have to be more creative, way more creative to compute this integral. Why substitution doesn't work anymore? Because the minute I put x cubed, I cannot capture the derivative of the inside. Substitution collapses. So that's how delicate substitution is. We need the function, and we kind of need its derivative to be part of the integral up to a constant. Only constant, we don't worry about it. But the minute I put x cubed, the derivative is x squared. I will have an x hanging in here. I will have trouble knowing what to do with it. So this is a case, even though I did small change, the substitution will fail in this case. Okay, so it's really settled. It's really settled. We need a function, and we need this derivative part of the integral. Now we're going to look at 37. 37. Integral of secant square secant square 10x plus 7. Okay. Now we shouldn't let secant square actually bothering us, because we should remember here that, so on the side, what's the antiderivative of secant square x? Not 7x plus 10. What's the antiderivative of secant square? Anybody remember? Which is the function whose derivative is secant square? Tangent, absolutely. Okay, so we know the antiderivative of secant square, but I don't have secant square x. I have secant square 10x plus 7. I have an issue. I have an inside function. And the chain rule tells me that when you have an inside function, things don't work simply. There is a chain rule involved. So again, my inside has to be put to be my u. That's for inside. And I know the derivative is not problematic because the derivative is just a constant and we can take care of that. So my du is the derivative of that, which is a 10 dx. And knowing where I'm heading, I know that I only have a dx, so I'm going to divide by 10 because I know that my integral does not have the 10 part. It only have the dx part. So to be able to get the dx, I have to divide by 10. And now we do the substitution verbatim. This should be the secant square u, and this should be 1 over 10 my du. Now I can take the 1 over 10 out. I will be left with the secant square u du. Now we know the antiderivative of secant, but now this is u is my variable, it's not x. So that's 1 over 10 tangent u plus c. And finally, this will give me 1 over 10 the tangent of. Since that's an indefinite integral, the variable is x in this problem, it doesn't have to be, and then we stayed with x. Okay. I hope this is okay. Clarify the substitution because, as I said, it's one of the most important integration technique you will learn. Now I look at 44. What is 44? Okay. Integral of e to 2x over e to 2x plus 1 dx. Okay, so again, it looks scary, absolutely, but we're gonna get it. All right, ideas. What do you see? Okay, a lot of students are suggesting to make the u to be basically the denominator. So, and is it a good suggestion? Is it a good idea? We always have to connect dots in those problems. So we really have to start thinking. If u is this, e to the 2x, its derivative is actually right here. So the derivative is 2 times e to the 2x, which is really right here. So you can think of this as an inside function, or you can rewrite it in this form and it becomes crystal clear as an inside function. If you want, you don't really have to go through this step. But if you rewrite it this way, you immediately see I have an inside, and the derivative of it is part of the integral up to a constant. So again, we're going to put, I will talk about the last choice. So we're going to put u equal e to the 2x plus 1. So the du is the derivative of that. So derivative of e to the 2x, because we need the chain rule, is 2 e to the 2x. Because remember, it's the derivative of the outside at the inside times the derivative of the inside, which is the x. And now I'm ready to substitute verbatim, kind of, because I know that it is this 2 hanging in there. So this is going to be equal to. This piece is the easy piece, that's the u to the minus 1 times e to the 2x dx. That's the leftover piece if you want. E to the 2x dx, I know that this is, I divide by 2 in here, is the half du. This is the half of the du. And now I have exactly what I'm looking for. Now the half could be taken out, and I will have, remember, u to the n, when n is -1, we have to be careful because that's going to give me the natural log. Then it's a half ln of u plus c. And finally, it's a half ln of e to the 2x plus 1 plus a constant c. End of the problem. Okay, I'm going to make a small comment about the last choice that was done on chat, which is correct, but you will see what the issue with it. Okay, let us say, suppose I did, which is very fair. So I have this integral. And it's very fair that we pick u to be e to the 2x. Why not? Its derivative is looking at that. Then suppose I do this. So the du is 2e to the 2x dx. And now I substitute verbatim. Let's see what do I get. Equal to e to the 2x, that will give me u plus 1. To e to the 2x in the numerator, this is going to give me basically my half du. So this will, I can pull the half out. So what we're doing is absolutely correct. U plus 1 du. But now here's the issue. Even though that's a simple scenario, here's the issue. I have a new integral in u. To evaluate this, because I have u plus 1, I will need another substitution. The chain rule, chain rule, chain rule, chain rule. What's the derivative of e to the 2x? So remember, we have to remember, our exam is coming up. What's the derivative of e to the 2x? Remember, that's a composition of two functions. That's your inside, and the exponential is the outside. So what is the derivative? Is the derivative of the outside, the e, evaluated at the inside, times the derivative of the inside. To be very careful, which is e to the 2x times the derivative of the inside, which is equal to 2. All right, that's how we get that. So remember the chain rule. Please start reviewing. Okay, now I go back to here. So if I follow this, then I will actually need another substitution because I have u plus 1 in the denominator. I don't have a u. So I can introduce another substitution. I can call it, I cannot use u for the variable. I can call it a t. And then I will have, okay, let t be u plus 1. dt is the du. And then I have to proceed. This will become integral 1 over t dt. Okay, so I can make this choice, but then I will have another substitution to do because it's u plus 1. So finally, it's a half ln of t. Then I will have to back up to ln of u plus 1. And sometimes you will have to do those as we move on. And then this will be a half ln e to the 2x plus 1. Okay, so if we make this choice, e to the 2x, which is a very fair choice, makes a lot of sense, I will have the u plus 1, then I'm forced to do another substitution. So by picking u to be e to the 2x plus 1, it means by picking it to be the whole denominator, the problem became a little bit faster. That's really the distinction between those two substitutions. Okay, any other questions on chat, please? Okay. All right, I'm going to give you 2 more, and I want you guys to do them before I move on to the last idea. So this should be simple by now. Suppose I give you cosine theta over 4 plus 3 sine theta and d theta. Okay, so this is not from the book, it's just some drill problem. Okay, I'm going to give you two of them. All right. Each one of you, how would you do that? Do you see stuff? Do you see things going on? What do you see?
I just want to make sure the bottom part is 4 plus 3 sine theta, right?
Yes, absolutely. So what do you think I'm going to pick my u to be? Exactly. I have to pick it to be the 4, the whole denominator. The whole denominator. 4 plus sine theta, because we see that if this is that, its derivative is the cosine, which is actually staring at me in the numerator. And then here I compute the du. You have to do it carefully. It's a 3 cosine theta, derivative of 4 d theta. That's the derivative. And now verbatim, as we did before. So this is equal. As I said, you can rewrite it like this if you want, because rewriting it makes you see very clearly an inside and the derivative of it, part of the integral, and then we do equal to. All right, now this piece is my u. The cosine theta d theta, I want to substitute it. I have to divide this by 3, and I will get 1/3 du equal to the cosine theta d theta. So this would become 1/3 d theta. And now we do what we did. It's a third 1 over u, oh, sorry, du. du 1 over 3 ln of u plus c. It's 1/3 ln of 4 plus 3 sine theta plus a constant. Now, 4 plus 3 sine theta is always positive because the maximum value sine theta takes is 1. The minimum is -3. So you're having 4 plus at minus at most 3, which is positive. So this we can actually even take the absolute value away. Sine theta. Okay. Now we check by taking the derivative here. If I take the derivative of my answer, let's see what I get. Okay, 1/3. Derivative of ln, let us remember the chain rule. This is an inside. So the derivative of the ln is the derivative of the outside evaluated at the inside. You multiply it by the derivative of the inside. Okay, which is equal to 1/3, 1 over that. So I'm trying to check that it's correct. Times. What's the derivative here? Derivative of 4 is 0. Plus derivative of 3 sine theta is the 3 cosine theta. The 3 and the 3 cancel out, and then I will end up with the cosine over 4 plus 3 sine theta, which is exactly what I want. Okay. All right. Today, we're going to stay along the same line, so last thing, but the only thing new, not new, is if I have a definite integral, which is a number now, and I use substitution to find the antiderivative, how shall I proceed? So that's really the idea we're gonna do. So how to do substitution with definite integral. So substitution with definite integral. So remember, definite integral is a number. So I have really the limit. So for definite integral, as we said, the definite integral is nothing more than this net area. And to evaluate it, the tool to evaluate it is to find the antiderivative of f between a and b. That's really the tool to evaluate it. So I take the antiderivative and then I evaluate between a and b. Okay. When I was grading your quiz yesterday, some student did not take the antiderivative. I still have a few papers I didn't grade. I'll do them now. So some students did not take the antiderivative. They took little f and evaluate between a and b. And be very careful. That's absolutely wrong. You need the antiderivative and then you do the evaluation. Right. So let us say now I have the following integral. Evaluate integral from, let us say, 0 to 2 of the square root of 1 plus 4x dx. So now it's a definite integral. And I need to evaluate the antiderivative. And then once I find the antiderivative, I take care of the limit. We're going to do this problem in slightly two different ways. First, I need the antiderivative of this function to apply the chain rule. So I'm going to isolate that and I'm going to compute the antiderivative. So that's the first method. And I'm going to do it in two ways. And we have to learn both ways, okay? Now, how to compute this integral? Because first I need antiderivative. That's a typical substitution because I have the 1 plus 4x. So I make my substitution. Suppose u is 1 plus 4x. The du is the derivative of that, which is a 4 times dx. And if you ever forget the du, you just compute du dx equal to 4, and then you multiply by dx. So this is equal to, now I am after this piece right there. That's the piece I'm after. So this is equal to integral of the square root of u times, I don't have the derivative of the inside outside here, part of the integral. It's a constant, as I said, does not really give me an issue. So I divide by 4 across here, and that's what give me 1 over 4 du equal to. So I'm just finding antiderivative. So I can apply the fundamental theorem of calculus. U to the power a half du means 1 over 4, 1 over a half plus 1. I'm finding the antiderivative. I don't put c because I know at the end I have definite integral. So the c does not really, it's not important here. This is going to give me 2/3 u to the power 3/2. Now I have to go back to x because that's an integral in x, but 2 to 1, so I will have 1 over 6, 1 plus 4x to the power 3/2. So now I'm this here. I'm doing that only. Now, since I found the antiderivative, I apply the fundamental theorem. So now the integral from 0 to 2 of equal to 1 over 6 times 1 plus 4x to the power 3/2 evaluated between 0 and 2. Right. Equal to 1 over 6 times the value at the upper minus the value at the lower. So it's going to give me 1 over 6 times. At the upper, sorry, if x is 2, I will have 1 plus 9 to the power 3/2. And at 0, I have 1 to the power 3/2. That gives me 1 over 6 to be 9 to the power 3 half. It means 3 squared. It means it's 27 minus 1. It means 26 over 6. End of the problem. Okay, so basically I applied the fundamental theorem verbatim. But I know that to find the antiderivative, there's a substitution involved. So I computed the antiderivative totally after I computed, and then I applied the fundamental theorem of calculus. Okay, that's the first way we can do that. Now there is another way we can do that, and that's how it works, the second approach. It's basically the same with a small change that's gonna take care of the limit at the beginning. So another way to do it. I hope you guys will not mix them up. The second method is based on the following. Okay, not the second method, second approach. So there is a theorem, I'll state it, but then I will tell you what is it about because it's usually hard for us to use it. That if I have a definite integral where substitution is in order, so the same scenario we have an inside and its derivative, then this definite integral is f of u du, where my u is g of x. So this is my f of u, and this is my du. That's where this is coming from. But it's equal to the integral of that. But here, I can put g of a and g of b. In other words, what this is telling me that if when you do the substitution, if you change the limit, so if x equal to a, you change the limit and you say, okay, if x is a, u is g of a, and if x is b, u is g of b, then this definite integral in x will be equal to this new definite integral in u. Okay, so let's see what I am talking about. So for example, suppose I'm computing this integral, the same one. Okay, I definitely need the antiderivative, which involve a substitution. But that's, so we're gonna use u equal, I'm gonna write this down here, 1 plus 4x. That's substitution. The du is 4 dx. Nothing changed so far. The only thing here, I'm gonna change the limit. We're gonna change the limit. I mean the upper and the lower limit, and never go back to x. We change the limit and we never go back to x. Go back to x. Let's see what do I mean by that. I mean the following. If the lower limit is 0, x equal to 0, my upper limit, sorry, u will become 1. So I'm substituting 0 for x in u. Now, when x is 2, that's the upper limit, then u would be 1 plus 4 times 2, which is equal to 9. What this theorem tells me is the following. If I change the limit, then this definite integral, which is, remember, it's a number, is equal to this new definite integral. Integral from, if 0, it's a 1. If 2, it's a 9. Of the square root of that, which is the square root of u. The dx is 1 over 4 du. So exactly like last time, the only difference here that I've changed my limit. I make them from 1 to 9. If I do that, it means if I change the limit at the beginning, once I have an integral in use, the new limit, I don't have to go back to x. So when I change the limit, I make a substitution, and I change the limit, I'm going to have a new integral in u. And when I'm going to evaluate this, I never go back to x. So if I change the limit, I forget about x. That's really what the idea is. So let me finish this problem so you understand what I mean. I don't go back to x. So this will be equal to 1 over 4 integral from 1 to 9 of u to the half du, which is equal to 1 over 4. Antiderivative of u to the power a half is the 2/3 u to the power 3 half. But now my new limit is 1 to 9. I don't go back to x anymore if I changed my limit. So now I only work with u. So this will be 1 over 4 times between 1 and 9. So this is going to give me 2/3. Sorry, I don't need those anymore. My apology. 2/3, 9 to the 3 half minus 2/3, 1 to the 3 half. Okay, I don't go back to x because I changed my limit. And finally, I'll get 1/3 times 2/3. 9 to the 3 half is 27 minus 2/3. Now the 2/3 could be actually factored out because 2/3 and 2/3, and I will have 26 inside. And then for 2, I will end up with 26 over 6, which is exactly what I got before. Okay, so let us summarize the two approaches. The first one, you find the antiderivative as usual. So you isolate the integral. You forget about, you don't put the limit. You take the integral. You find the antiderivative as a function of x. And then you use the fundamental theorem when you compute the definite integral. So first approach, you don't change the limit. You take the integral, evaluate it as a function of x. You find the antiderivative. After you do that, you go back to your definite integral and you apply the fundamental theorem verbatim. The second approach is fairly similar. The main difference is we change the limit. We don't only do the substitution. We actually substitute for the limit. So we change the limit at the beginning. Once we do that, this old indefinite integral is actually equal to this new definite integral. And then I compute this new definite integral in u, just like there is no x anymore. I forget about x. And then this is a new integral in u, and we evaluate it. Okay, that's the difference. Let's do another problem along the same line. Also, I will do it in 2 ways. Okay, I will pick an easy one, I think. No, I won't pick an easy one. Evaluate the following. And I will try to do it with and without changing the limit at the beginning. Okay, so integral from 1 to e, remember e is just the number, of ln squared over x. Okay, we're going to evaluate this definite integral. And I'm going to do it the first method, which is find the antiderivative and then apply the fundamental. Do not change the limit. So the first method is just I go after the antiderivative by itself, and then I apply the fundamental. All right. What's a good substitution here? Do you see inside? Do you see outside? Can you make any connection within this integral? Do you see something going on? Do you see an inside and this derivative staring at us? Or this derivative part of the integral? Anyone? ln of x, absolutely. ln of x, this derivative is 1 over x. So if I rewrite this, because at this stage you have to start really seeing things. So this is basically 1 over x, that. Okay, and this suggests that, if you take u to be ln, its derivative is really staring at you. So we're going to take u to be the ln du.
I have a question.
I'm listening.
Couldn't you also rewrite it as ln x to the power 2 times x to the power -1?
Yeah, I can do that. The only thing I will lose is I don't see the 1 over x immediately. Understand what I mean? I want you to see, I want you to be able to see something and its derivative. The minute I see 1 over x in a way and I see the ln, I want you to connect the dots. I want you to see that this is the derivative of that. You understand?
Yeah.
Yeah, so you're right. You can write x to the minus 1, but I'm afraid if I write it like this, you don't see immediately that x to the minus 1 is the derivative of ln. And I really want you to connect dots in those integrals, see function and see its derivative staring at us. But you can do it, no question asked.
All right.
Okay, so this is gonna become equal to this piece is the u square, and this piece is the du. Simple as that. So this is nothing more than 1/3 u to the power 3, but I just want the antiderivative in x because I did not change my limit, ln of x to the power 3. I don't care about the constant because eventually it's a definite integral I'm interested in. Now I go back to my indefinite integral. Sorry, my definite integral. This is equal to the antiderivative. Now that's my antiderivative evaluated between the 1 and the e. Okay? Equal to. I need to make a remark here. The antiderivative at the upper minus the antiderivative at the lower. Okay, it means 1/3 ln of e to the power 3 minus 1/3 ln of 1 to the power 3. And now we're done. ln of e, it's a 1. This is a 1 minus ln of 1, it's a 0. And I get 1/3. Okay, all right. Question. Now the second method, which is almost the same, but I will do one thing different. So, I mean, we have substitution. So the second method goes like that. And you have to be comfortable with both because people use either one, depending which one they think it's easier. The second method is like this. So I have, again, the same integral. And the only way to evaluate the antiderivative is really substitution. That's really the only way out. So the second approach is we do the u the same, nothing changed. The du is the same. Okay. The only thing is that I'm going to change limit. And then I'm going to create a new definite integral with a new limit. So change limit and never go back to x. What do I mean by change limit? I say here, if x is 1, my u is ln of 1, which is 0. And if x is e, my new limit is ln of e, which is 1. So this means that the integral from 1 to e of ln of x squared times 1 over x dx, because it is a substitution, you have to treat it as such, going to be equal to the 1, we take the ln of 1, which is 0. The e is now the ln of e, which is a 1. The inside is the same thing what we did. So this is going to be u squared du. Now, this new definite integral, I evaluate this new one, u cubed. But now we use the new limit and we don't go back to x anymore. We don't need to go back to x anymore because I changed the limit. And then I will get 1/3 times 1 minus 0, which is 1/3. End of the problem. Okay. All right, so for tomorrow, you guys will have problems again, substitution, which was the same idea. And with this, I actually finished this course. So we will not definitely do anything else. I want the substitution to be under your belt very well. And tomorrow, I will do two things. I'm grading your quiz. There are some subtle mistakes. I will have to address them. And my idea is tomorrow, start, bring with you exam 3. And I'm going to review exam 3 with you. Is that clear? So tomorrow, bring exam 3 with you. And once we get the substitution under our belt and answer all your questions about it, then I would like to review exam 3. I know where your weakness is and I'm going to address them. All right? Any questions?
I have a question.
Start on your review. You don't have a lot of time. I'm sorry you have your exam on Monday. There isn't much I can do about it. Please don't slack. You don't have time for that. Go ahead.
When do you think our quiz will be graded?
So you're probably the ones that I graded almost like 70% of them. So
Okay.
it should be done, of course, today.
Okay, sounds good. Thank you.
Sure. Any other questions? All right. So if you guys have any questions, my office hours are right now. Please meet me in my office hours. Bye.